Last time we started talking about these Braverman-Kazhdan spaces, which are XP, which is P derived on G. And in fact, I mean, in general, you can take G to be any split reductive group. But we were focusing on the case where G is split, simple, and simply connected. And I went through a bunch of examples of what what these spaces look like. And the point is that you should think of them as some sort of generalization of the notion of the vector space. And they're a place where one can play with the ideas of harmonic analysis and analytic number theory. Okay. So last time we looked at the local picture, and I gave some hints as to how you define the spaces XPFV for places V. And so now I want to go to the global picture and talk about Poisson summation. So now I'm going to let F be a number field. This isn't so important. You could also take it to be a function field. We can define BXPV, a so-called basic function in the short space for almost all V. Okay. I think, in fact, you can define it for all V, and one way to define it is just in terms of stipulating what the Mellin transform is. If you give me a Mellin transform, then it'll give you what this function is, and then we'll set X P A F to be equal to completed tensor product over all V dividing infinity of S X P F V tensor S V not dividing infinity. You have to do a restricted direct product in this case. F V, where here this is the restricted direct, restricted tensor product with respect to these basic functions, B, X, P, V. And I'm not going to give you the definition of the basic functions, but I did give you an example, the example of the cone, and the general flavor is somewhat similar to that. It sort of very much wants to be the integral points of the scheme, but somehow the singularities force that to be some perturbation of that, right? So then, let's see here. Theorem, due to Braverman and Kazhdan, that's based on the Langlands, is that if we assume that we have some F equals FV1, FV2, FV1, V2 in our short space, and this is this convenient notation where this means I'm looking at the function at V, and this is the function away from V. And I assume that FV1 is compactly insupported and smooth on the open part. V1 and the Fourier transform P op of FV2 is exactly supported and smooth on P op FV. Then you have the expected summation formula. X equals sum over X in F of FP P op F X. And let me just remind you from yesterday that when P op is the opposite parabolic, so if my parabolic started out as being upper triangular matrices, it's then the lower triangular matrices. My Fourier transform most naturally goes from one space to the other. Now you can remove the assumptions on the F and deal with general elements in the Schwartz space, but then the answer involves residues of Eisenstein series. Somehow that's a bit unsatisfactory. It really should be a sum over some space that's related to XP. Okay. But I won't go into that problem. Okay, so let me talk about the proof, because I mean the theory of Eisenstein series in general is very difficult. This is part of what Langlands won the Adel Prize for, was this work, and the decomposition of the L2 space of the adelic quotient using it. But in this case, it's actually pretty straightforward. So here's the strategy. All right. So I guess what you try to do, maybe step one, prove when P is equal to a Borel. And step two, reduce to this case. And I think at least in some examples, I mean, this would be observation that the proof is much simpler in this Borel case goes to Langlands, but I mean, Rehrman and Kazdan wrote this down in a very nice way. And the best way to understand it is via an example. So let's take B. So I'll look at the case where G is equal to SL3 and U is equal to the derived group of the upper triangulars. So U of R is just 1 star star 1 star 1 in G SL3. So all the upper triangular matrices. And then XB op, or sorry, XB0 in this case is SL3 mod U, and XP I can think of as just being the set of vectors U V in R cubed cross R cubed, such that U transpose V is equal to 0. So in other words, their dot product is equal to 0. And how do you see this? Well, I mean, this is an easy exercise. If you take SL2, SL3R, take some G in it, map it to R cubed cross R cubed, E3, G inverse E1. Then this gives you, I mean, this is going to be, it's going to induce the bijection between SL3U and the open orbit in XPR. Okay, so this induces XB, the open orbit into XB, right? So now how do I get a Fourier transform out of this, and how do I get a Poisson summation formula? So there's this really pretty idea. So let's look at XB. It gives, I have two maps to a vector space. So one map forgets the second coordinate, let me call that P1, and the other map forgets the first coordinate. Okay, so then the fiber over a point P1 is U cross the perp space to U. And the fiber of V over some V, P2 is V perp cross the V. Both of these are two-dimensional spaces. And they have a canonical SL2 equivariant form. So you just take V1 comma V2 and you map it to U1 tensor U2. And to be fair, you have to be a little bit careful with your measures in order to sort of make this actually, you need this sort of forms to vary in a family, but let me not get into that. the point is that you can apply Poisson summation along the fibers. So each of the fibers of these two maps is just a two-dimensional vector space. And so for each one of those two-dimensional vector spaces, you can apply Poisson summation. And so you get a Poisson summation formula for the whole space. The definition of the Schwartz space actually implies that if I take F in the Schwartz space, then F restricted to say U cross U perp is going to be an element of the Schwartz space of U perp of AF. And this is just a two-dimensional space. It's AF squared, right? So, I mean, we know how to do Poisson summation in this space. I mean, it's just a vector space. All right. So this is how, I mean, and the generalization of this idea handles the Borel case. So this handles P equals Borel. Okay. All right. So now, how do we deal with? How do you think of GA cubed mod 0 group theoretically in terms of BU, etc.? It is going to be SL3 mod the mirabolic. So, so it's the stuff that looks, I mean, the space, when I'm looking at just one of these things, GA cubed, then the space I get is, I mean, it's SL3 mod everything that looks like 0, 0. I may have to put it back like up or down or something. I mean, the zeros may have to go somewhere else depending on how I choose my base. Okay. All right. So now what you can do with this is, okay, well, this doesn't tell me how to handle other parabolics that aren't Borels. So how do I deal with things that aren't Borels? And actually, Bremer and Kauschen handled this case of Borels first in the paper called the Schwartz space of basic affine space. It's also based on some unpublished work of, I think, Gelfand and Grea, but I'm not sure. So how do you deal with the general case? Well, for the general case, you construct a diagram. Let's do like SL4 mod B derived for the Borel in SL4. I can push this down to say SL4 mod P22. So this is the, or P22 is the parabolic that looks like this stuff. So zeros here. I can do my whatever Fourier transform I want over here, and then I can push down to SL4 mod P22. And if I choose the correct Fourier transform up here, I have choices now, because there's Fourier transforms for sort of, I mean, in group theory language, there's Fourier transforms for every simple reflection, but I mean, we don't need to get into that. And what you have to do is you have to construct a map that goes between these two spaces, and that's your Fourier transform for the maximal parabolics, or any other parabolic for that matter. And so the second paper that they wrote was sort of giving a nice interpretation of what this map is. Okay. So this is a reformulation of I mean, in essence, these Poisson summation formulae are all elementary, and they're all induced by just understanding Poisson summation formulae on fibers. And so maybe a moral here is what you might call the fiber bundle method. And this is to construct transforms, say Fourier transforms or Poisson summation, can proceed if you have a fiber bundle over some base where the fibers admit a family of transforms. I mean, David explained this to me, and I think this is sort of, well, I thought this was a beautiful idea that you can make this work. And one thing that's fun is that, I haven't worked this out, but I don't think that you have to actually take the appropriate Fourier transform up here in order to get it to descend appropriately. Okay. All right. So that's sort of the sketch of the proof of the Poisson summation formula. GGPS. Gelfand, Graya, Piatescu, Shapiro. GGPS. Okay. All right. Okay. So now I want to spend my remaining time talking about beyond Braverman-Kazhdan spaces. So I can. Right, and there aren't so many examples. I wrote down all the known examples for you earlier on in this lecture series. I want to talk about the case of triples of quadratic spaces. Okay, so I'm going to give myself 3 quadratic spaces with di equals the dimension of vi equals even. All right, and by quadratic space, I just mean dimension di, vector space, and a non-degenerate quadratic form of them. Sorry, a non-degenerate symmetric bilinear form. And then, it determines and is determined by the associated quadratic form. Just Qi of u. Right? I'm going to set V to be the product of VI and YR, Y in VR, such that Q1 of Y1 equals Q2 of Y2. Okay, right. So there's a solid understanding of the Poisson summation conjecture in this case. And this is an interesting case because the singularities are no longer points. This is not a Braverman-Kazhdan space. So, this is sort of really a new example. So, and the references here are, I work with Guiying Liu, I work with Chun-Chen Su, my graduate student, and then a follow-up work with Liu and Spencer Leslie. All right. So in this case, we have short spaces. We have Fourier transforms Fy going from it to itself. And we have a Poisson summation formula for many F, although it's not as developed as it could be. You still have to make some assumptions on F locally. There's still some things, some open questions that we're thinking about. For example, is SY FV local? So in other words, is it somehow described as functions that have some sort of singularities as you approach the different singular loci? And that's still sort of up. up in the air, and if it's not, there's sort of a way to correct it so that it is, and then the question becomes, after doing this correction, are you destroying some other nice properties of the short space? You have to check that you're not. Okay. So what I'm going to try to do, and I may not get through all of it, we'll see. So I want to give the formula for Fy. I want to define the short spaces, and I want to give the proof of the Poisson summation formula. Okay, so I have to say, which is really amusing, is that logically, in terms of these papers, and actually the only way I know how to prove these things, is actually to prove this first for something that's a substitute for the short space. Then I give the definition of this and prove that the Fourier transform exists. So the way that this is structured is you prove the Poisson summation formula. There's an indirect proof that the Fourier transform exists, and I might get to that later. And then finally, once you know the existence of the Fourier transform, then you use its properties to prove a formula for it. So it's quite interesting and I actually don't know how to proceed in the opposite direction. So let's start with the formula for the Fourier transform. All right, so I'll set some notation. I think this is really interesting because, again, this is sort of the first example where we know something about these Fourier transforms outside of these Braverman and Hausdorff spaces of the vector space. And you can see already that the situation is quite a bit more complicated than in the case of Braverman and Hausdorff spaces. So I'll give myself a tuple of elements of F times. So here I'm taking F to be local. So F equals FB. All right. I'm defining brackets A to be A1, A2, A3, and R of A to be A1, A2 plus A2, A3 plus A3, A1, square root over brackets A. And I'm going to choose a top form on the smooth locus of Y, such that omega Y wedge d Q1 minus Q2 wedge d Q2 minus Q3 is equal to dV, where dV is giving me the Haar measure. So the same thing I did for the. Okay, so now I want to isolate a subspace of the short space. And so this is the image of the restriction map from the short space of FV to the short space of YF. And it's non-trivial to prove that, I mean, there's something to check to show that actually these elements are in the short space. So at this point, I haven't even defined for you what the short space is, but okay. So for this subspace, I can give the following formula for the Fourier transform. Okay. So for F in this subspace, F, Y, F of C is equal to the integral over F times psi Z inverse integral over F times cubed pi bar squared R A. Okay. I'm not going to put parentheses on these things, but the order actually does matter here. It doesn't converge if you don't do the order correctly. See. 1. Okay, and then finally times factor q chi qa over 2 minus 1 d times z. Okay, and here, I mean, this a d over 2 minus 1 is just the product of a I equals 1 to 3 of a I d I over 2 1. And the q, chi q, I mean, these are some Hilbert symbols. They're just quadratic characters. So if your quadratic forms are split, then they'll just be trivial. Okay. And finally, maybe I'll say one more thing, but C, that thing. A is C over A1, C2, C3 over A3. All right. So maybe, you know, a few remarks are in order. Okay. So the first thing is that it's manifest that this is more complicated than the situation in the case of Braverman-Kazhdan spaces, because instead of just having a composite of a bunch of operators that are essentially given by Fourier transforms, you have another family of operators that are given by this integral over f times cubed. So there's this rational function that came up here that's printed here that's playing a role here. There's this factor here, which is qc qy. But you still do see some things that are similar. You still see sort of natural pairings that are occurring on your space, and you're integrating the function against those natural pairings. I mean, at some level, one thing that you can think about this sort of function theoretically, and you can say, or maybe in terms of invariance, and you can say, well, I'm looking at some space equipped with a group action. I'm looking at things that I want to be invariant under a certain group action. You can compute how many invariants you have in those situations. And somehow the Braverman-Kazhdan space, there's not so many invariants, so there's sort of not so much wiggle room. And then here, there's more invariants, so there's more wiggle room. Okay. So I was originally hoping that it would be, you know, a little bit simpler to work with, but you know, it's just not. And I mean, this indicates that there's new phenomena going on here. So one corollary of this is that if F is non-Archimedean, then Fy is unitary, and you have a Plancherel formula. So this was pointed out to me by Chunshen, and it's part of this paper, sort of. Okay, right? And as a remark, you should be able to prove this in general. But we can sort of use a bit of a hack in the non-Archimedean case. The elements of the Schwartz space are all going to be finite over under some compact open subgroup, and so it gives it sort of a degree of smoothness. In the Archimedean case, the analog should be something like Sobolev theory for this space plus some analog of Maury's inequality. Chunshen pointed this out to me, that this is what one should need. I mean, this should certainly exist, but you know, at that point in the paper, we were somewhat exhausted and decided to leave that to a different occasion, or maybe he'll write it up later to try to figure out this theory. Okay, so this is what the Fourier transform looks like in this case. Let me give you the definition of the Schwartz space. All right, so it uses the Weil representation. So let me just, so let me remind you, and it's hilarious when people say remind, especially in a course. I'm writing a book right now, and Sol Friedberg made sure to tell me that I should never say remind because you're supposed to be telling them in the first place. Anyway, so let me tell you what the Weil representation is. So yeah, I should say I'm writing with not me, we. So here's the definition of this Weil representation. The representation of SL2F on the short space. And in order to give you what this representation is, I can give it to you on a set of generators. Okay. And then of course you have to check that it's compatible. One can do that. DT. So the fun thing is that this matrix 0, 1, negative 1, 0 acts via a Fourier transform. The thing that's very useful for us is that when you look at upper triangular matrices, they act via a character F of V. All right, and this one's going to be, this right here is going to be crucial for us. And then finally, scalar matrices sort of act via, well, I'll call it chi qi of A. It's some quadratic character times A to the dimension of Vi over 2 F of A V. Okay. So what's really neat about the Weil representation is that you start with a and I mean, it can be generalized to the symplectic group, but you start with a representation that's geometric in nature. So you're just scaling down here. This is just some representation of this maximal torus. You start to add something to it by something abelian in this case. And then it turns out you can extend it to this, to the whole group. And it's pretty amazing that this thing exists. So, so this commutes with the action of the orthogonal group of the quadratic space. And in fact, it does not commute with the similitude group, but there's a certain semi-direct product of the similitude group and the SL2 that acts. Okay. So now I'm going to look at a very special type of Braverman-Kazhdan space. I'm going to look at SP6. So I'll write it down in this form. It's my G and GL6R, such that G transpose 0 I3 negative I3 0 G is equal to I3 negative I3. All right. And then I have a nice embedding from SL2 cubed into SP6 that's just given, if I write my coordinates AI, BI, CI, DI, that's just given by setting this to A1, A3, D1, C2, C3, D1, D2, D3. Okay. So now I'm going to let P inside SP6 be the Siegel parabolic. Right, and what is this? It's the following parabolic. I mean, I gave you a description of all the parabolics earlier, but with everything I've set up here, it looks like the following. So this is, the G is its Levy subgroup, and the Z is part of its unipotent radical. And here G is in GL3, R and Z transpose Z to Z. So this is our thing. All right. And it turns out that SL2 cubed, well, this thing embeds into SP6, like we just said, and it acts with open orbit on XP naught, which is P derived, SP6. I'm going to pick X naught to be a base point for this open orbit. And let me just remark that I can choose, oh, okay, maybe I'll make that remark in a moment. So given this data, so I started out with, let me just sort of remind you, sorry if this makes you motion sick or something, but I started out with a Weil representation, and then I gave you an embedding of SL2 cubed into SP6, and now I'm going to combine these two objects. So how am I going to combine these two objects? I'm going to define a map from F cross VF to smooth functions on the smooth line. And the map is just going to be giving, essentially by integrating out this action. So on pure tensors, it'll be given by integral over X naught SL2 cubed F of F1 G rho G F2 of C dot DG. So the dot means I'm plugging something into this variable, right? So I'm actually going to make a choice of X naught, and I'm going to choose X naught. So the stabilizer, and I mean, you have to check that this is possible, but it is. So the stabilizer is N naught of R, of all matrices of the form 1, T1, 1, 1, T2, 1, 1 minus T1 minus T2, 1. Where the T1 and the T2 are in R. So you get this funny subgroup of SL2 cubed. Okay, so let's think of this construction for a moment. If this is going to be well defined, then this expression has to be invariant under the action. So this G, if I put something in the stabilizer of X naught on the left here, it's going to come out here. And so the expression has to be invariant under that action in order for it to be well defined. And this is it is well defined precisely because we're evaluating this thing on points in Y. So why is that? Let's go back to our Weil representation. So how does this thing act? It acts via minus T1 minus T2. F of C is just psi of T1, 1, T1, T2, Q2, minus T1, T2, 3, which is just equal to F of C if C1 or C is an element of YF, right? Because then this expression right here, everything is going to cancel out. Okay. All right. So now how do I define the Fourier transform? So the Fourier transform, so this, okay, so I guess I have to tell you, step back for a moment and just say that S of YF is defined to be the image of this map I, where I is defined up here. And it's this map from these two short spaces down to my smooth locus. Right? So how do I define SY given that? Or sorry, how do I define the Fourier transform FY given that? FY is defined to be a unique map such that following commutes. So I'll call this fx, and this is I. This is I. This is y. All right. So on the top, f of x acts on the first factor, and f of x is just a normalization of fx. Let me write it this way. It's fx of f of x is, well, it is f p naught f of w naught inverse x for some vile element w naught. I think you can even take it to be the element that's giving you your symplectic group. Okay. All right, and let me point out that it's not obvious that this map Fy exists. And the only proof that, I mean, I'm sure there are other proofs of this, but the only proof that I know is via a global to local argument. Okay. Okay. So now, given this preparation, let's derive the formula for the Fourier transform. So the input that we have is this diagram here, and we want to give the formula for the Fourier transform. And it's kind of fun how this works out. So if I give myself some c and y smooth of f, I'll let f c of g be rho g f c, where g is in SL2 cubed of f. And I'm going to extend by 0 to xpf. So let's see, maybe I should, okay, so that's what I mean here. Remember, the SL2 cubed is an open dense set in this space. So I just extend it by 0, I get some measurable function. Okay. And then I'll give the formal justification. And I always found, it always bothered me that formal means the same as informal in this context. But the formal explanation for this is the following: that Fy of f, by the way we set things up, it is Fy of I Dirac at x naught tensor f. Okay, because if I formally plug in Dirac at x naught and I apply this integral, then I just get f back. This is I of f xp delta x naught tensor f, which is the following: x dx. Okay. I haven't really done anything yet. I mean, in this step, I'm using the fact that SL2 cubed is dense inside xp. And I will apply Planck's rule at this step, which is known for these Braverman-Kasdan spaces. And I get xp of f delta x naught of x f xp f c minus x dx, which is fx negative x naught. Okay, and so now what I do is I just use my previous formula for f of x that I explained in previous lecture to compute this. So compute. All right, so this outline, it turns out to give the right answer, but it's complete garbage because this function Fc is not in L2 XPF. I mean, in fact, if you think about what's happening with the Weil representation, you have this entire unipotent radical that once you take norms, it's acting trivially. So you have to apply some truncation. And then in every one of these steps that are involved in this formal derivation here, you have to make sure that when you execute, there's actually two limits that occur in the truncation. You have to make sure that you can switch limits. The details take something like 33 pages. And the lead on this was Vincent Su. I mean, I don't know how I would have finished this if he didn't take the initiative and get this done. I mean, there's actually some really nice ideas that go into that he thought up to get this thing to work. So, okay, so this is sort of a hand-wavy justification of the Fourier transform. Okay, so let's talk about how you prove the Poisson summation formula in this context. So, all right, so for F satisfying certain local conditions, sum over all y and y smooth, f of y is the sum over all y and y smooth of okay. So let me sketch the proof of this. So in one sentence, and maybe I'll just say it in words, you take three theta functions and you plug them into Garrett's integral representation of the triple product L function. Okay, so if that means nothing to you, then I'm going to go through the argument, but that's the one sentence proof of this. So here's the more sentences proof of it. So we start out with a theta function, right, which is this theta f. I've given myself some f that's in the short space of V, all right? And the fact that the Weil representations exist allow you to prove, together with Poisson summation on the vector space, that this is a function on SL2 cubed f on SL2 cubed f. No, it's left. The point is it's left invariant under SL2 cubed, right? And so then what you consider is the following thing. I give myself F1 tensor F2. It's in and then I look at the following. All right, and here I'm using the typical notation, brackets G is GF, not GAF, for any of the groups that I'm working with here. All right, so let's recall that SL2 cubed has a unique open orbit here. So if I, under some support conditions, this turns out to be equal to the integral over n naught of f mod SL2 cubed AF F1 of x naught G F2 G, right? And what I'm using here is that the only orbit that matters under some support conditions on F1 is the orbit of X naught. And the stabilizer of that orbit of X naught is M naught. Okay, so then this is one of X naught of G times the integral over M naught. Sum C M G G. And the point is that this integral here, for the same reason that we discussed involving the action of the Bay representation, this thing vanishes unless C is an element of Y smooth F. Okay. I mean, rather than go back up, let me just write down what the key computation is here. This is somehow the key point that makes this thing work. If I take this, I get integral over T Q1 C1 plus T2 Q2 C2 T1 minus T2 minus T2 Q3 C3 times F of C. All right, and remember, I'm integrating over T1 and TAF, T1 and T2. So I use the fact that if I take the integral of my non-trivial character and I integrate it over this additive adelic quotient, I get 0 if alpha is not equal to 0 and 1 otherwise. Or I mean, if I normalize the measures appropriately. All right. So ultimately, out of this, you get that maybe I'll put this on the next page. You get that the integral over SL2 cubed of sum over X in XP naught F of F1G rho F2 dg is equal to the sum over all C and Y smooth I F1 F2 FC. But we know that missing X on left-hand side. Yes, so I want to put XT. Okay. That should be a cube, right? On the other hand, this top thing by our other Poisson summation formula is equal to the integral over SL2 cubed sum over X and XP naught of F of Fx F1 XG times theta F2 G dg, which is the sum over all C and Y smooth F I F1 tensor F2 Fx. All right, so then the equality of this and this is exactly what you want to prove in the proof of the Poisson summation formula. All right. Okay, so I think at this point, I just like to, I mean, this is the end of the lecture series, and I just sort of like to recap that, I mean, my point for this was to propose new venues for investigation. And I mean, in particular, this this non-abelian delta soup, and then this new world of summation formulae. And I mean, one thing that David Koshner commented to me once is that, I mean, you know, the primary motivation for me and for him, I think, for starting this study is towards the Langlands program. But these objects and these transformation formulae should be important in a much broader context. And so this is this seemed like a nice venue to sort of explain some of these things to, you know, an audience who has the tools to make inroads if they decide to take a look at these sort of things and use them from the context of whatever analytic number theory that you know is your primary interest. I mean, there's just a whole new, you know, whole new world of places that you can investigate new ideas and apply old ideas to new scenarios. And so that was sort of the point of this. Yeah, I'll stop here.